Hi, everyone. Welcome to this next session talk. We will have Sebastian Wild. He is a assistant professor at the University of Liverpool, and it's also his first PyCon conference. So let's give him a welcome.
Yeah. Hello, PyCon. It's great to be here. Who of you knows that Python 3.11 comes with a new sorting algorithm? Prior to seeing my abstract? Okay, a few hands. Nice. Yeah, you wouldn't normally want to be worried about that because it doesn't matter how you call the sort function, what's going on behind the scenes. But in this talk, I want to show you what's going on behind the scenes. I want to give you a little bit of the history and the technical bits of that. So I'll split the talk in basically two parts. First, it will be fluffy stories and nothing too harsh. And then in the last part, I do want to show you the actual algorithm that's now in CPython, and hopefully soon in other libraries too. So reserve a little bit of mental energy and caffeine for that last part. Just finished my coffee, so we'll see how it goes. But let's start simple. Why do we do sorting? Is often a building block for many small tasks. We can make searching faster. Good old phone books used to be sorted, not that they're anywhere in use still, but we do the same on computers. We can clean data, it's the prime method to remove duplicates, and many more fancy algorithms. Think of computational geometry, if that's your field. There's many places where sorting is just a coroutine, some subroutine that you do to speed up other things. So it's no wonder that Python also has a built-in sorting method. And it's basically two ways how you can call that. You can take a list and call .sort, or you can use the built-in function sorted that gives you a copy of your list which is in order. Now, order, you have to specify what that means. There's either a natural order on the elements that you have in your list, or you use the key parameter to specify what there should be ordered by. And if you've seen Valeria's talk yesterday about all the cool functional programming tricks, there's a nice little helper. If you prefer to give a function that compares two items and returns which one is smaller, you can do that and turn that into one of these functions, of these key extractors that match the Python API for sorting. That's pretty much the end of the Python-specific part of this talk. It's a bit awkward for a PyCon, I guess. The rest is, if you want, theoretical computer science, which is also where, I guess, my field is in my daytime job. There's a nitpick I want to mention because it's relevant for selecting the sorting method, and that's stable sorting. I want to just show an example application which wouldn't work with an unstable sorting method. Suppose you have these Simpsons characters, first name, last name. You want them in sorted order by last name, and among those with the same last name by first name. And you could do the following: sort them by first name, and then sort them by last name. And you would hope that after that, all those with the same last name still have their first name in order. For this second sorting step, this would only work with a stable sorting method. Stable here means if there's two elements that compare equal, according to this key extractor function, then a stable sorting method keeps them in the order that they appeared in the original input, and that's what you want here. And some other methods famously don't preserve this property. A little bit on the history of what CPython had implemented to sort. Very early on when it started, I guess out of laziness and or convenience, it just referred to the C library, which is, as the name says, CPython is implemented in C, so it was natural, I guess. Then there were a few iterations on this. All of these algorithms are still modifications or variants of Quicksort. And Quicksort famously isn't stable. And then at the time, this became a big ask from the community of Python programmers that we should have a stable sorting method. It was just inconvenient for all these applications like the one I've shown. And Tim Peters, who was already active on sorting before that, then came up with the now relatively well-known Timsort algorithm, which is a stable sorting algorithm and has many other interesting properties for those of you who know. It remained almost 20 years without many major changes. At least the core algorithm wasn't really touched, with a few exceptions that I will come back to. But then last year, a slightly more fundamental change was to include our algorithm Powersort. And I'll explain what that is and where the daft name comes from. Just as an aside, Timsort was the name started as an inside joke among the core developers, and wasn't really a Tim's choice, but it stuck. And once the algorithm was exported to other libraries, it became known by that. So be careful with choosing your names. I tried to give a name before I published the algorithm so that this is off the plate. To appreciate the changes, let's have a look at what Timsort is like. And the Canadian friends, so I did a postdoc in Canada. That comes up on the slide later again. That relation is not just a superficial one. Let's take a step back. We want a sorting algorithm for something like CPython. We have basically two choices, two textbook algorithms that many of you will know, Quicksort or Mergesort. And simplistically speaking, Quicksort is fast, it's living up to its name, and it's in place, but it's not stable in the usual implementations. And Mergesort is also reasonably fast and stable, but not in place. It usually needs extra space to be efficient. Now, as an aside, that's the algorithms research in me speaking. You can get stable and in place together, but it's quite tricky. It's not a standard textbook algorithm, and they're quite slow in practice, so they're just not competitive. That's just an aside. So it seems like in other instances in life, you have to decide, pick any two, but you can't get all three. Python has a lot of objects, and everything's an object. Everything's a pointer to an object, virtually. So a little bit of extra space maybe is not such a big deal. So it seems sacrificing the in-place property is the better bet. So we want something based on Mergesort. Just in case you don't know Mergesort, here's a little non-verbal description of the algorithm. Shout out to my friend Chandra Fekete, a professor in Germany, who created with a former student these very lovely illustrations of algorithms. Let me run through this just for Mergesort. You sort a list by taking the left half and the right half and recursively sorting each. And once you come back, you merge these two sorted halves by taking the first element from each, comparing them, and then the smaller one goes to an output space. Because these sub-problems were sorted, the first elements in each are the smallest in their subproblems, so the smaller of the two smaller of the smallest is the smallest overall. If you keep doing like this, you will get the list in sorted order. Timsort, by and large, is this idea on steroids. There are several optimizations here on the slide, and I just want to list them because I think the algorithm is essentially great because it combines all these things. But I don't want to go into details for this talk, just the parts that are relevant is, number one, we try to pick up sorted runs in the input. If there are segments in the input that are already in order, we would like to keep those and not sort them again. If we want to do that, we need to decide how we do that. So if we find those runs, we have to decide in what order do we merge them. In the classic way, that would be just dictated by the recursion. Now that we give up that approach, we have to decide that somehow else. And this last bit will come up later. I've tried to write very small, concise Python code for the core idea. Don't take this as anywhere close to the CPython implementation. This is just to illustrate the idea. If you want to see the full code, including all these method functions I left out, is on a Colab. I don't want you to read the code in detail. I just want to point out the main principle by which Timsort operates. You work through the array once left to right in one big loop. Then in each step, you find from the current position the next run. How does that work? You just scan forward. If the elements keep increasing, you go on until they stop increasing. Or if they're decreasing from the start, that's also fine. So you keep going until they stop decreasing. That's your run that you found. And then this run is thrown on top of a to-do list. It's a stack of runs that you still have to merge. And you may delay some of these tasks for a later time, or you may merge some things now. That's what is governed by these rules. So you throw the new run on the stack, and then you go through these rules that tell you what to do. For example, the first one says, if the new run on top is longer, so these bars, that's the length of the run, if that one's longer than the third, you should merge the second and third. If that's not the case, you keep checking with the next rule and so on. And if neither of the three rules is applicable anymore, you go on and find the next run. The idea behind these rules, or the goal for these rules, was to establish this kind of invariant. Don't worry about the details too much. It basically says every run should be at least as long as the two ones on top of it combined. Now, why exactly that rule? One nice consequence of that is that the stack cannot grow too big because you essentially exponentially increase the runs. If you look down the stack, the run lengths grow exponentially, so you can't have more than some roughly logarithmic number of those. Why exactly these rules? Well, Tim even publicly confessed, so I'm just citing the bug tracker here, that he didn't spend so much time on working on those. It was the first thing that kind of worked, and he decided to stick with it unless there was a good reason not to, and at the time there was no good reason not to. Unfortunately, there is a good reason not to. Remember this invariant that I mentioned, the Fibonacci thing, everything's bigger than the two above? And it turns out that's not quite true. These rules don't guarantee that. That only popped up, so this algorithm was in CPython and in many other libraries from roughly 2002 on. In 2014, a group from the Key project, which is a Java formal verification tool, where you can specify your preconditions and then you try to prove the postconditions. And they were at the stage where they said, okay, we're done with toy examples. Let's do some industrial strength code. And it's a Java tool, so they picked something from the Java library, namely the Timsort implementation in OpenJDK. And they tried to prove it correct. They tried to prove that the library actually sorts. And it kind of failed, and it kept failing, and then they dug deeper, and they found, yeah, for a certain pattern of run lengths, this invariant is not guaranteed to hold. And even worse, Python and Java both chose this stack. They implemented this with a fixed size array because you could prove it never grows bigger than something based on the invariant. But the invariant wasn't guaranteed to hold, and so the stack could grow bigger, and you could get this nice exception in Java. Something similar would happen in Python if you just had big enough arrays. That's not great, right? You don't expect your sorting algorithm to just crash. There's a fix for that. They basically found the same people who did the formal verification. They found if you add another rule, then that solves the problem, and you indeed get this invariant. You can even, that's something I didn't mention before, there was a little asterisk on the order n log n worst case time. You would want that the Mergesort implementation is order n log n, but that wasn't obvious for this one either. It was proven eventually, but it's a long and complicated proof. So at this point, you may wonder, does a sorting algorithm have to be that complicated? But at least the problem with this stack overflow was fixed. But there's another problem that popped up a little later. And when this paper came out, that's when I got interested in the problem. It turns out for a certain pattern of run lengths, Timsort does really stupid merges. Namely, these red ones always just add one single element to a fairly long list to make it one longer. And it does all these reads and writes for just making very little progress. You can do much better with some other order of the merges. I will explain what these trees mean in a second in a bit more detail. The point here is if you make n bigger, you pay 50% more than you should. It doesn't feel right. So at this point, I remember this old software engineering saying, if you're riding a dead horse, get off. So maybe there's a more first principle fix for this choice of merge policy, of the order of merges. That's just waiting to be found. So as an algorithms researcher, what do? We first define the problem formally, say what we want, and then try to look in the literature if someone has solved it for us. And it worked perfectly in this case. So what do we need? If we want a run-adaptive merge sort, something that finds these existing runs and then merges them, basically 2 steps. You find the runs, and you merge them in some order. And that's up to you to decide which order you want. Now we can narrow down this a little bit. We only want to merge 2 runs in a row, so everything is a two-way. And because we want a stable sort, we are only ever merging adjacent runs. You can think about that if you merge something, the 1st and the 17th run, you will mess up stability. That means all these merge policies can nicely be represented by a binary tree. If that's your input, these are the runs. And now maybe the merge policy says, merge these 2 first. OK, I'll do that. Here's the result. And that's 1 node in a small binary tree. Maybe the policy now says, take the result and merge it with the 1st run. OK, let's do that. And you see how you attach this node with the 2 things that it merges as its children. Now let's keep going. So this is an arbitrary, I just made this up, so it doesn't have any specific meaning. And once you have the root where the entire list is sorted, then you're done. In the rest of the talk, I will not draw these numbers. We don't care about the elements. All that counts, or all that is important here, is how long these boxes are. So a merge policy is nothing but a way to choose such a tree. The last thing we need is a way to say which of these merge policies are good, which do we like. So we need a metric for the cost. And here you can just take the total length of all those gray boxes in the middle. So that's the total length of all the written merged results. That's roughly the number of memory transfers, so maybe that's a reasonable measure. And it's an upper bound for the number of comparisons. That's also convenient. So that's the problem. Now, this maybe doesn't look like something that's already known. Here's a quick example that this indeed makes a difference. By the way, if you don't pay attention, you can create a merge sort variant that has quadratic runtime, so you want to pay attention. There's a connection that maybe isn't completely obvious, but once you've seen it, you can't unsee it. We're basically asking for an optimal binary search tree, which is a fairly well-known programming exercise. You would give this to students to practice dynamic programming. So it turns out that the best possible merge tree, the one that minimizes these merge costs, is exactly the optimal binary search tree if you're given weights on the leaves, on the null pointers. Right, so you can imagine these are the keys, and then there's gaps between the keys, and these have probabilities of access. That's the tree problem that's behind it. Then there's a lower bound, so I thought I have to have at least one non-trivial formula on the slides, but I'm not using it for anything else. It's just cool to have a lower bound. Now, at that point, that's a well-known problem, so I kind of knew the literature already, so that was lucky. So I could just go through the options. There's this quadratic time dynamic programming algorithm to find the optimal tree. That's not really interesting, it's way too slow. But there's a little lesser known literature on nearly optimal binary search trees. And these are typically quite simple, greedy algorithms. They're very quick linear time methods, easy to implement too. And they're almost optimal in this sense that I don't want to talk about. And one of those is called the bisection method, and that is the basis of Powersort. I tried to find an intuition for this method, and you could say it kind of rounds the merge tree to a completely balanced tree. I'll get a bit more specific on the next slide on what I mean by that. The original description of this method is recursive, but if we want to combine this with Timsort in the way we had it before, this march through the array once and keep a stack of things still to merge, you can't really use this recursion. So my contribution was to come up with a way of implementing this method without recursion. And here's what I came up with. This may look a little weird at first. I've explained this algorithm quite a few times. It's 5 years old by now, at least the core idea. And I changed how I explain it several times because I felt it was not quite successful. You'll be my judges whether this works better. Here are your runs in the input. Here's a perfectly balanced binary tree. And we like balanced trees, so we would like to have something that's close to that. Now, how do we get that? Because the actual runs we have, they lie anywhere, so we can't just follow this tree without breaking up the runs. And we don't want to do that. So let's do the following. We take the middle between the middle of all these runs, and then for any two adjacent runs, you have such a blue interval between the midpoints. And now we let these blue lines slide down until they hit one of those green poles. The green poles are just the nodes of this perfectly balanced tree drawn up to their level in the tree. There's nothing very, very complicated. So there will be some sticking up high up in the tree, and others will sink down further in the tree. You can already see the ones that represent cheap merges of short runs, they sink down more, but this is all just magically happening. Okay, if you have that, you can take all those poles that are still left, and they give you a subtree, and that's the one that we use. Now it's convenient to note at this point, the poles all have a number. That was just the level in this virtual tree. And we can assign each boundary between two runs this number. And that's the power. It comes from, there's a power of 2 involved in computing those numbers. I'll show you later. It was just a good name. I don't know, I'll be honest. The thing is, if you have those numbers, if you just know the depths of all of these boundaries, you can reconstruct the merge tree. Maybe that's not obvious if you see it first time, but you have to believe me then. What we really see is that these nodes move where they belong between the two runs, but that's the same tree. And this would be the merge tree that we get from this. That's just a different way of drawing this. Last cool property about this, these blue numbers are completely local. They don't depend on all of the other runs. They just depend on this run and this run that defines the blue interval. And the rest is independent. It doesn't matter how the rest of the input looks. And that's the vital bit, because we need to be able to check this in isolation. Good. That was the trickiest bit. Now, I have an example to show you how the full method looks like. Again, this is also in this Colab. Don't try to read the code too much. Just follow the example, and hopefully that gives you the key idea. It's similar to Timsort. The key difference is we have to scan one run ahead of time, because we always need 2 runs to determine this power of the boundary. So we'll start finding one run. Ignore the 0. That's just a boundary case to make things work out conveniently. The first real case is we find the second run and find the power between the two by sinking down this blue line and throw it on top of the stack. Timsort had these 3 or 4 rules to decide if the stack is okay. We have a simple rule. I always want, if I look from the bottom up, I want to see powers strictly increasing. That's my rule. Very simple stack invariant. As an aside, at this point already, you can easily prove from that the maximal stack height is just log n, because the powers are in this balanced binary tree, so that's at most log n deep. And because I want to have them strictly increasing, I can have each power at most once. End of the aside. Back to the example. Here, 3 is bigger than 0, so we keep that we're happy. If we do the next one and put it on top, this is not strictly increasing. So we have to do something. We have to get rid of the 3. And that's the point where it tells us we have to do a merge. So we do that merge. And whenever you merge 2 things, it inherits the smaller power. Then the stack is fine again. We can go on to the next one. The same thing happens. The 2 is in the way, so we have to merge this. Then the stack is fine again. We scan the next one. This has power 2. We can stick it on top. Nothing happens. The next boundary has power 4. We can again stick it on top. Nothing happens. And once we're done through the list, we just merge top down, the topmost 2 repeatedly until we have just a single run left. You made it. That's Powersort. That's in Python 3.11 now. You will. That's the key part. I'll skip how to compute the powers really, because it's once you worked out how these blue lines fall down, it's pretty straightforward. Here's the definition, and you can do some bit tricks to get that faster. But I think that's not the interesting part of it. Again, the Colab has the details if you want to see that. I thought instead you were interested in what this changes. If you measure the number of comparisons, then we usually see a small improvement, sometimes a larger improvement. I have some more data to show, but maybe because in the interest of time, I'll skip it. If you look at the actual running times, it's a bit more complicated. I've seen quite a variability in moving between different machines. I've never found an input where it gets substantially slower. Almost always it got faster, and sometimes substantially faster. And I think that matches also what happens on the algorithmic side. A last bit, that's a little bit of an advertisement for the rest of my work. Timsort has been implemented in various libraries, and some have switched to Powersort already. Now, in some of these frameworks, the costs are a little different. In CPython, comparisons are relatively expensive because that needs to go back to the interpreter and so on, whereas moving pointers around is cheap. In, say, something like Rust or Java, that's different. And here, it might well be that we want to merge more than 2 runs at a go, because that saves memory transfers. It happens to be that Powersort is very well suited for that. It's very easy to generalize. I won't show you how, but you can take my word. And I spent a lot of time on analyzing Java's dual pivot quicksort, where the same story happened. It uses 2 pivots instead of 1 to save memory transfers. Let me wrap up. You've seen Timsort. It's by now the standard, the stable method of choice in practice. The original merge policy, I think, just wasn't the right decision or the right thing to do. And we now have a clean solution. So for me, that's the end of that story. That's at least the hope. I would love to see Powersort ported to all the other libraries where currently Timsort is used. And there's 2 candidates within this community that I would hope we can approach, even though they don't only use Timsort. And then the second bit is, from an academic perspective, I would be curious how much this adaptive sorting business helps in general. So how many inputs do have this partial sortedness? Or is sorting used at all in your application? So here's my request. Help me by donating some of your data. Run some exemplary Python application that you have. We created a custom CPython version. You find how to do it on my blog, where you can run your code, and it just keeps track of all the things that got sorted. To be precise, it stores a list of integers that has the same comparison behavior as your data. So I hope that means you don't worry about giving that away. So that would be my ask for you. Hopefully we can make a little benchmark out of this to just see how much practical applications have these pre-sorted lists. Thanks for your attention. I hope you enjoyed that and you learned a little bit about Python's new sorting algorithm.